handling. So I explained so far this unsupervised tracking, right? Now, keep in mind that initially I explained the segmentation-based tracking. The first one, if you look at this difference, this was my segmentation-based tracking. That is, every region in an image was first segmented in both temporal domain and spatial domain, and then took the union. This is called segmentation based. And I segmented result, I put a tracker. In the next model that I explained here, it is called rule-based classification-based tracking. So I had different rule bases based on my learning mechanism. Those rules are granular level rule base. And then based on the rule base, I made classification. Now the one I will say is called prediction based. Prediction based. So here what we'll do, its a beauty is that it's unsupervised and it is handling complete occlusion. In my previous one, I didn't consider the concept of occlusion. This was overlapping, but not complete occlusion. So here I'll use it for as it's called a prediction based method. So previously it was segmentation based method. I segmented image and I put a tracker. Then I got by a classification by method. I formed every image in terms of certain granules, and every granule I just classified based on certain for better performance. Now I'll go by prediction. So here again we will consider the spatio color neighborhood granules. That means given an image, I consider the granules in terms of spatial similarity, color similarity. Then I compute for every frames, a sequence of frames, a neighborhood rough filter. This is a new concept. What is the output? It gives rough estimate in terms of lower approximation of the location and and the color model of objects. So that means if I have p number of previous frame, for every frame corresponding, I will get a lower and upper approximation indicating the location of the objects and as well as the color model. That means it's values, gray values of the models in terms of lower upper approximation. And this lower and upper approximation for p previous frames of the objects I will use for the p plus next frame. So if it is ft to t minus p, then ft plus 1 frame, I will use this model information in terms of their, I will model the nature of variation in terms of size, speed, that is the displacement, the direction of objects, and then we locate the object in the next frame. And with the next frame, again, it is characterized by lower and upper. Lower means definitely, and upper means definitely as well as possibly. And in the object regions with minimum roughness, if I have, I'll just track it as my tracked region. And if this roughness is not minimum, we compute an instant entropy which indicates the amount of occlusion. That means then I take the occluded region, I put it in the lower and upper, and then say, see in which way the uncertainty becomes reduced. And that's how I changed it handles the partial or just total accuracy. That means I minimize the boundary. I minimize because whenever I get the minimum roughness, that means there is no doubt. But wherever my roughness is not minimum as indicated by threshold, then I see that means some occlusion is there, occluded region. That means my boundary is wide. So I reduce the boundary again in terms of some intrinsic entropy, which quantifies the amount of occlusion. So that's how I got it. Now what do we do theoretically wise? So let me refresh. Neighborhood rough set incorporates neighbors information in heterogeneous feature space. And since the neighborhood granules are overlapping, they are suitable for modeling the overlapping characteristic of data. Therefore, we need to define the size of the granule. Granules will be automatically formed given threshold values phi and the distance function 1. This slide I have explained before. So what is the filter characteristic? I take input to the filter two types of temporal information corresponding to each frame. One is take TF frame, T to T minus 1, T to T minus 2, T to T minus 3, T minus 4, and so on. And I take their union. So I get one frame. So this is what is called delta P. Then I take delta I, T to T minus 1, T minus 2, T minus 2, T minus 2, T minus 3. So it is a consecutive. One is T to all frames difference. Another is T to a consecutive one. So if I take consecutive, I get P frames. And if I take this one P frames, I take union. So convolution is taken between two types of change in the information and which it executed to label, to identify, to determine which temporal segment will probably belong to which object in a certain frame. I'll explain. And output a neighborhood filter is, it gives an estimation object in terms of lower or upper set. And then we compute the velocity and color model. That means to at which rate the object is moving and their color models and the different object in sequences. So what we do, I take a T current frame and we have got P total number of previous frame. So I take the difference between consecutive frames in granular level. All are in granular level. That means I compute all those granules such that the intensity value of this granule minus its previous frame, I minus 1, is greater than equal to threshold. So that constitutes a set of granules. It's called spatial color granules determined by threshold T1. And this spatial color granule X and I minus 1, basically spatial temporal granules form around the point X in two consecutive frames. This. So at T1 is the temporal threshold to detect the change. That means every frame I take its difference from the T minus 1. Similarly, I to T minus 1 to T minus 2, T minus 2, T minus 3, and so on. And I form this granule with respect to some threshold T. Of course, T1 has some impact. I will explain later on. So that's how I take the difference between two consecutive elements. Then I take difference from current frame to all previous frame. That is T to T minus 1, T to T minus 2, T to T minus 3, T minus 4, so on. So I take this all such granules, a difference of T from these all previous frames greater than threshold T2. So this indicates another temporal threshold to detect the change region from current to all its previous frames. So I get Ti delta P value difference from current to previous frames. I get the difference delta I and P. So to my input to the neighborhood filter will be union of the change region among current to previous. So I take its all union to current to all previous frames. This is one input. And P change region between consecutive frames. This is another input. So this is one frame P, and here it is P frames. Here it is one frame because I take union over all P frames. So I take one P frame, and here it is P frames. So then I take 1 to P point convolution in the filter to result in a P point matrix. But this P point matrix would have two parts. One is lower and upper. Since two approximate decision spaces over the filter are defined, there will be two P point output matrices. So this is the filter design. You input output relation delta I, that is P matrices, one matrix P, take convolution, it gives input output lower approximation of the object model in previous frames, upper approximation of the object model in previous frames. And this convolution operator is nothing but lower and upper approximation. Convolution operator is union and intersection. So if I take the intersection operation, I get the lower approximation. As usual, because if I take the minimum values, lower approximation. And so by definition of lower upper approximation will be, I take the union intersection My lower approximation is all granules belonging to the universe such that these granules belongs to IC. So all granules belonging to the intersection between these two frames. It determines the lower approximation. And for upper approximation, all granules belong to the universe such that the granules belongs to upper, but it has non-empty intersection of the lower. It belongs to upper approximation UC. I do not call it upper approximation, it is UC, that means which is resulted from the union, but at the same time it has non-empty intersection with the lower approximation. So that's how I get the lower approximation and upper approximation, where NX is the spatial color granules belonging to delta P and delta I. So this is my filter design. So as an example, I can see for P equal to 3 frames, previous 3 frames, you can see this is my delta I, and this is union of the delta P. I take the convolution. This is my lower approximation, upper approximation. That means of the object models, objects, this is the definitely belonging to the objects. This is definitely as well as possibly belonging. So out of this, so convolution results in 3 by 1 matrices, 2 types of approximate region of the object region of the filter. And from this lower and upper, I can compute the roughness. I can compute the velocity, that is change of information from frame to frame, here to here. Similarly, change of information, change of location. From that, I compute the displacement. I compute the velocity, acceleration. I again form the granules. And with the help of this granule, in the next frame, I find the location of the predicted object in terms of lower and upper approximation. And so performance of the, what we do, the performance of when you have a filter, what is the performance measure? That we borrowed from electrical engineering. Signal to noise ratio of the NRS filter is 20 log 10 cardinality of lower approximation divided by cardinality of upper minus cardinality of lower. So if you see that cardinality of the object set, lower approximation, we can call it as a signal or amplitude of the signal. And this can be considered the cardinality of the boundary sets, that is probable noise, I call the amplitude of the noise sets. So we like to have higher signal to noise ratio. So lower value of signal ratio will give me poor filter performance. So I like to have always high value of signal to noise ratio. Now here comes the significance of those threshold T1 and T2. I mentioned one. So suppose this case signal to noise ratio becomes poor. So then I cannot use it. I need to have larger value. That means I need to increase this value and decrease this value. So role of T1 and T2 comes here, and P, number of frames. So if value of is much low, then what does it mean? That it can be assumed that the smaller than the exact region was extracted out. So region should have been more larger, but you have extracted low. So in that case, the delta value should be decreased. So if you threshold the delta value, the similarity value, similarity difference, if T value is now lowered, then we will get larger number of pixels as an object model. So if lower approximation value, the cardinality is much low, then T1 should be decreased. Similarly, if the denominator is much higher, we need to make it lower. But this is fixed, so we make it, this is value lower. So in order to make it lower means that it can be assumed that the extracted change region from delta P is large than what required. That means we need to lower it. That is, the value of T2 needs to be increased. So if we increase the value of T2, that means less number of pixels will be detected as my region. So even after doing this, if we see that signal to noise ratio has not improved much, if neither the signal nor the noise gets much deviated, then their expected values, but still signal noise is still low, that means then P needs to be increased by 2. So if it is 3, then make it 5. If it is 5, make it 7. you have to make odd number so that you can compute the median also. So the entire process is then repeated. So here comes the significance of T1, T2, and P in order to characterize the signal to noise ratio of the filter, because we need larger value of this signal to noise ratio to have just better performance of output. Output means object model in terms of lower and upper approximation. Having this tracking methodology, so we have filtered over P frames, and it has provided a rough estimate of the approximated locations and color. Color model means intensity values of the object. I got it. And this initial information are then used for estimating the object location in the next frame, that is PFT+1 frame. So what we do, we model the nature of variation in size, speed, and direction of the object from initial leveling, and define velocity granules, neighborhood granule, acceleration granules as well. Different means displacement, and it's a rate of displacement gives acceleration. And use this granular information to find the approximation in terms of lower and upper of the object model in FT+1. And then you compute the object roughness. If object roughness is low, that means object is clear. You track it, no problem. If it is large, that object is occluded. Then you compute the intrinsic entropy on boundary. That is on the occluded granules only. To ensure, because how do you compute the boundaries? Because you know upper and lower, upper minus lower boundary granules. Ensure the presence in the object model and track the object region. And intrinsic entropy quantifies the amount of partial or total occlusion. So here is the block diagram. This is a initial labeling, tracking. What is initial labeling? We have all previous frames. From that, we have spatial color granules. Then from frame to frame difference from T-1 to T. That means you compute those delta I or delta P. Then you form the neighborhood of filter. Then from that, you get lower and upper approximation, compute signal to noise ratio. If signal to noise ratio is high, then you accept velocity and acceleration granule. If it is low, again, you increase P equal to P+1, you come here. So this output velocity and acceleration granule, you put it here and take the next frame FT+1. Here also you go granule, you compute first spatial color granules. Then with this input and with this level which you have learned, you use together to find the object model for the FT+1 in terms of lower and upper. Again, you compute the object roughness. If it is low, you track the region. If it is high, compute entropy and minimize the boundary. Simple. So for tracking in a new frame, object locations are approximated with velocity acceleration granules obtained in initial leveling. Low object roughness means object is clear, you track it. High roughness means object is occluded, you then compute intrinsic entropy for the boundary granules in order to ensure the presence of their object set. After that, object is tracked. This is a London Metro. Look at this, frames per second 15, and P6 is the previous number of frames. The guy is first. This is a complete occlusion by the pillar. It got. The guy is a little slower rate, is moving. So it is based on prediction, I mentioned you. There is no classification or segmentation concept, as we mentioned before. So it's a complete occlusion by one. Similarly, it's a laboratory image. This image I will show again for the deep learning. Laboratory image, the two guys, they are completely occluded. See, they occluded, but still they are considered as two objects, not as one object at this stage. This is integrated by two different trackers. Similarly, long duration tracker. So this shows that how beautiful it was. Now I'll explain the application of this lower approximation in bioinformatics. Just I'll take one example. Time. You know that prediction of gene, prediction of microRNAs, and so on. So I will consider one example. There are so many applications of fuzzy clustering and biobasis determination. The fuzzy equivalence partition means for gene selection. Here I will consider only fuzzy rough entropy in microRNA ranking. MicroRNAs are basically those genes which actually opposes the formation of protein. So here we will use crisp and fuzzy granules. It explain I will use user and upper and lower. You remember again, lower means definitely belonging, and upper means definitely as well as possibly belonging. So relevance of lower approximation in case of bioinformatics and microRNA ranking. Now, what are the challenging areas in microRNA ranking? This is a very recent paper. So here you have got small sample, large dimension. Usually in case of pattern detection problem, when we started working in 70s, our basic assumption is the number of samples should be much, much larger than the number of features. That's how when we started working in speech, our number of samples was about 900 or 1000, but number of features was 2 or 3. But today, you have got the other way, topsy-turvy. The number of features has increased, but number of samples increased. For example, you go to hospital or doctor to give your sample only when you are sick. When you are normal or patient, you do not go to hospital. So obviously, number of normal patients sample is smaller usually than the number of disease patients. For example, the cancer patients, and the number of total sample is much more than the larger dimension. Here is the microRNA. If it is gene, then the number of feature available data that we get from machine learning repository. So here the challenge is small sample size, large dimension. And another interesting thing, all the microRNAs that you get, they are not equally important for cancer detection. They may have some different roles, but to segregate from normal to cancer, that means they are expression values. You see, because they are obtained by microarray technology, which provides expression values of microarrays. So the expression values, change in expression values, they are significant for cancer, and those expression value changes only to a very small number of microRNAs. That means we need to find out those microRNAs which are responsible for cancer detection. And here we will use set is crisp because you have to decide only cancerous or non-cancerous. There is no fuzziness. But here granules are fuzzy. That means same cancerous patients may not have the desired number of expression values. Similarly, that's why the granules are not crisp. Had it been the crisp that clearly cancer, clearly no, then the problem would have been very simple. But as you know, no, cancer has different stages. So here is the challenge, that means the granules are fuzzy. So we will use fuzzy rough entropy. And we will fuzzy lower approximation of normal and cancer. This is a supervised system. So I know the patients having normal and patients are with cancerous. And every patient has got same number of microRNAs. But microRNAs have different expression values corresponding to normal one. So we use fuzzy lower approximation of normal and cancer classes to find the probability of definite and doubtful regions for entropy competition. Because here granules are fuzzy, but decision making is crisp. So we'll find that probability, the relative frequency of definitely and doubtful regions for entropy computation. And we'll see that entropy minimization implies higher relevance of a microRNA. will show that 1% of microRNA provides significant improvement over entire set in terms of F score as compared to entire set of data. This is a very interesting result. If you take all microRNAs, they are not capable of giving good index values. On the other hand, if you top 1% as determined by the relevance of microRNA, that gives better F score. What is F score? That I will explain later on. Maximizing F score means you want to sure the cancerous patient should be detected as cancerous patient and normal patient should be treated as normal patient, not anything, because it's not a just speech recognition problem or image pixel recognition problem that if it is a wrongly classified, no problem, but it is a problem because if cancerous patient is treated as normal, then it is a bad thing. Even it is even worse if a normal patient gets treated as just cancer. That's why doctors use, medical practitioners or biologists, they use F score. They do not go by the classification accuracy as we go for our machine learning. But anyway, the F score is again dependent on those sensitivity, specificity, I will explain. So maximizing F score means you are ensuring mostly that cancerous patients should be treated as cancerous patients as much as possible and normal patients should be treated normal. That is, false alarm should be minimized and we show superiority of. So this is our CRIPS classes, cancer and normal. There is boundary, there is no fuzziness, but the granules are overlapping. Granules is overlapping. I call it normal patients, normal granules, cancer patients, normal granules. Now let's consider in simple case one dimension. So for every microRNA, say microRNA 1, if I take microRNA array 1 value, expression values for cancerous patients and all normal patients, I get this kind of overlapping. That means my boundary granules are overlapping, samples are overlapping, but my decision has to be crisp. So what do? We compute, let's compute the membership value of patient P to normal class, all patients. Similarly, membership values for a patient P to cancer class, mu n, mu p. And it is a normalized value so that membership values two together addition makes 1. Because that patient will be either from normal or from patient. So their membership values for both these classes you compute, and if we normalize them, then it will summation will be 1. Now, given this value, I can see, so for every value I have point every patient, whether normal or patient, I have membership values for both the classes. Now, out of those, I compute the membership value of this any patient P or belonging to the lower approximation of the normal class. Membership value for any patient, either normal or cancer, belonging to lower approximation. That means to an extent they are sure. Now, what is the extent that they can be considered sure to belong to a normal class? Here we compute by minimum value of the all membership values with 1 if the patient P has come from normal, because it is supervised. For these yellow patients, I take the minimum value of its all membership values for normal class and 1. That means from cancerous class, I take the minimum values of its all membership for the normal and minimum with 0. So that the values becomes all 0. So for any patient or belonging to normal lower approximation of the patient class that is sure to be a patient is a membership value of these normal patients for belonging to this class, because for others it is become 0. Similarly, I can compute for cancerous patients. Same way, take any patient's membership value either from normal or cancer. If it is from normal, then I take the membership values of the for cancerous scars and with 0. Therefore, it becomes all 0. But for patients coming from cancerous class, I take the membership values with respect to its own membership, minimum with respect to 1. So it gets this membership 1. So for membership values for any patient P or belonging to lower approximation, that means it is definitely cancerous, its membership value is determined from this one, others 0. So mu low n, mu p, p, c determines the degree of being sure to be a normal and cancerous patient. Please keep it a note of this. So for any kind of granule patients, I can compute, this is a supervised system, I can compute the degree of being sure to be normal and cancer patients from this expression. This will be 0, only will remain this, that is for patients from normal, their membership values, I compute a normalized membership value, that normalized membership value will indicate the degree of being sure to be a normal patient. Similarly, for cancerous patient, for degree of being sure will be determined by the normalized membership value of the cancerous patient, not 1 or 1. It's all membership values. So if I have this membership value, I can compute the relative frequency of lower approximation, that is the cardinality. So number of 1, I take the cardinality over all this, over all these points. Membership values, I take the summation and divide by 1 by n, the total number of 1. Similarly, I compute the relative frequency of lower approximation, which is called, basically it is the probability. For membership value, you are basically computing the probability. P and 1 by C, it is computed over all the samples. So it is a cardinality over C. That is number of cancerous patients, number of normal patients. So I have low lambda low C is a relative probability occurrence. We have got lambda low n. So from that, I can compute lambda 1 mean cardinality, that mean relative frequency of lower approximation is divided by 2. Similarly, I can use cardinality of relative frequency of overlapping regions equal to 1 minus lambda, because lambda 1 plus lambda 2 equal to 1. So I know that this is lambda. So lambda 2 will be 1 minus this. 1 minus this. 1 minus this plus this. So after having this, you can compute entropy by using logarithmic entropy function as entropy value of microRNA 1, considering normal and cancer classes, as lambda I log lambda I, where lambda 1 plus lambda 2 equal to 1. What is lambda I, lambda I 1? Mean cardinality of lower approximation region of normal and cancer, and cardinality of overlapping region. That means this is the sure, and this is the doubtful one. Okay? So after having this, I compute lambda 1 mean cardinality of lower region at the cardinality overlap region. And if you can see that if this value is lower, means separability between normal and cancer is more, increases. So this increases means separability between normal and cancer class with respect to microRNA M1 increasing. That means relevance of microRNA for cancer detection is increasing. So using this expression, I can compute the relevance of each microRNA and then rank them in terms of microRNA. And then I can take 1%, 2% depending on my need of microRNA. I do not need to consider entire microRNA. So that's how you compute the relevance. It's called relevance of a microRNA. So when you compute relevance of ith microRNA, I consider the separation between normal and cancer class. So separability microRNA decreasing means separability, lower the value of means separability between northern classes is increasing. The relevance of microRNA for cancer classification is increasing. Similarly, I can compute the redundancy of microRNA. That means if I take a set of microRNA, fine, but I want to see if there is any redundant microRNA so that I can remove. So redundancy, I can do the same redundancy with respect to another microRNA, MJ, where J is not equal to Y. So I compute the same expression, separability of MJ with respect to Y, and I compute FRM MJ and between. So here N and C replaced by N. That means to compute the fuzzy graph entropy corresponding to MI, that means is redundancy with respect to other microRNA, we consider M1 and M2 as two separate classes instead of normal and cancer. And here the number of samples of the classes will be the number of patients, same number of patients instead of cancer and normal. So I compute this, and then the separability more this is redundant. So I'll now look at this data set. I take the cancer types 6 binary data. Total number of microRNAs 309, 300, and number of normal patients 5 only. Cancer patients. If we look at this, usually the number of normal patients is always less, is gone, except this one. And the total number of patients is always less than the number of microRNAs. So that's why the classical patternization techniques that we have developed up to 80s, you can no way use now for this kind of bioinformatics data, because here the concept is changed already. So now you see the result, we compute, we find there this microRNA. Suppose I take 1% of this microRNA. Now I want to see that with 1% microRNA, how this entire pattern set can be classified. So for that purpose, we use the performance analysis called F-score. It's called sensitivity, specificity. What is sensitivity? It's a true positive divided by true positive plus false negative. Here it is specificity means true negatives by false positive. What is false positive? True positive is number of correctly detected cancer microRNAs. True negative means number of correctly detected normal microRNA species. What is false positive? That is the detected as cancer, but they are actually from normal. That is number of wrongly detected as cancer microRNA. Actually, they are normal, but treated as other one. Similarly, false negative means detected as normal, but actually they are from cancer. That is number of undetected cancer microRNAs, which you could not detect. That means they have treated as normal. Treated as normal. So our objective is to maximize data. So this is take a so it is a harmonic mean of this true sensitivity and specificity. So we want to maximize both. So our maximizing F-score means we want to maximize both this and this. That means true positives should be more and true negatives should be also more. That means cancer patients should be treated as cancer patients, normal as normal patients, not the other way. So here we see that Now you can see that results of this relevance of this 6 cancer type of data. We take all those microRNAs, number of microRNAs I mentioned 309, 360, etc. And I take 1% of the top ranked, is yellow mark. So you see that your top ranked is 98. So I'm showing here 1%. That is how small it is compared to 1. Now, if I take the F score based on the entire microRNA set, and the 1% is selected. See that 1% gives much larger F score value. Very interesting results. So what we do, and we use this using SVM. It's a very good standard classifier. So what we do first, F score for each microRNA is computed using leave one out method, and then the average over all such scores. That's how we compute the microRNA. Now you see that very interesting result. Only 1% microRNA, that means about 300, so 1% will be about 90. That means you take all microRNAs, you rank them individually as per the relevance and take a top 1%, and you see that top 1% gives highest. So if you take all number of, instead of 1% only, you give report. That means they create confusion. This is the significance of this result. Similarly, if you can see that there is when the number of sets increases, few thousands, then what you may have need to know the redundancy. So you see that 10% or suppose the selected set, and even 10% is a larger number. If you then let us consider 20% of the removed by the redundancy removal, 20% removed. So you see that after removal, it's not much changed. So even up to the 10% selected, even if you 20% removal, then also it's not much changed. So number of microRNAs. So classification again using support vector machine. And recently in 2021, we got this paper. It's called Identifying Drug-Resistant MicroRNA. That means which are the microRNAs whose expression value, if changes, then the cancer, they may not respond to the drugs. Understand one? So previous one was, which are the microRNAs, if their expression value changes, that means they are causing cancer. Here it is drug-resistant microRNA. Which are these microRNA? If their value changes somehow, then they may not react to the drug. That means drug will not be useful for them. See, these two characteristics are there. It was published in a special issue on machine learning on AI-enhanced healthcare and medical services. For one, that means they lead to the drug design and discovery. So you asked me last time that, sir, you keep an example. So I kept it in mind always because I will give an example one. Now, previous day I mentioned that in R&D drug discovery and one, it has a better role. It's a significant role to find one. Similarly, you can use this genetic algorithm searching and learning mechanism to find the optimal those molecules. Example I have shown from microRNA, only 1% microRNA top ranking microRNA, if you can find, you will give the better F score value as compared to considering all. Because you might think that, no, if I take all microRNA, that will be better result. No. Because all other microRNA, they may be useful for other tasks. But for cancer detection, responsible for cancer, no, they are not good. That's why here comes the significance of this machine learning or AI algorithm. And here I've shown how this relevance of lower approximation becomes significant in finding the definitely belonging to normal cancer patient in order to compute the uncertainty associated with each microRNA with respect to normal and cancer classification, with respect to determining the redundancy between two just microRNA in a group. So if you know the microRNAs which are responsible for cancer detection. If we know the microRNAs which are responsible for drug opposition, that means drug-resistant microRNA, then accordingly this will help us to go for drug design and discovery for cancer patients. Now, last part of my talk, very important. Where are this going to lead you? Because when you do some research, you have to keep in mind about 7 to 10 years ahead, where are they going to help you? First one is summary, they say. So basically, these are different machine learning tools, basically. What have we explained for the last 2.5 days? Machine learning tool. I have used it for video analytics in depth. One example in bioinformatics, but it can use for link prediction problem and so many problems. We have then your web intelligence, then you have a community detection problem, so many. So, for example, identifying drug resistance, I mentioned video conceptualization. There is an IoT. That means some patients you are, for example, monitoring at Singapore, and you are monitoring the old person's ECG. Suddenly, if there is a change in ECG, that will give a signal to you as a remote, and then you can supply the medication from India. This is through IoT, Internet of Technology. That means the same problem that I explained, that one, you are tracking something, suddenly another moving object came. So you are able to track it. So when there is a sudden change in the event, I call it event detection. That was a normal patient, no problem. Suddenly some changes in ECG, I call it event detection. So that newly term is called video conceptualization. That you are seeing a video, suddenly you see that certain event has occurred, which was not supposed to occur. So video conceptualization. Then neural network generation. That means generation of neural network is very important. You do not know where from you start. So here comes the significance of, say, your lower approximation. What lower approximation? That you know that which part of the data is surely belonging to this neural network. So to this region or class. So you take only this one, that is called pure sample. And based on the pure sample, you develop neural networks. There's a neural, then you train with the upper minus lower or by the upper. That means you allow the network to grow with the help of doubtful samples. Instead of considering the entire doubtful samples, that is upper region samples, to develop a network, you develop the network with a pure one, that is about sure, that is with data coming from lower approximation. And then upper, so that you have now learned from the bad samples also. So that's how neural network generation that will help use lower approximation granules to form the basic net and they grow by upper set. Similarly, social link prediction and so on. So what are they leading to? There are 3 things I can see, but it's not that easy. What is called computational theory of perception. Another is natural computing. Another is big data analytics. Now, what is computational theory of perception? That means you make computation based on perception, not based on any measurements. For example, when you drive a car, you use the perception of speed, perception of direction, perception of gap between the 2 cars, and so on. You do not measure every movement and then you drive, then you talk. Okay? So, and you see that this perception, because of this limitation in our sensing organs, biological organs, particularly human brain, they have their attribute values are granules. That means slightly left, slightly left. It's how you drive a car, and their boundaries are imprecise. That means they are fuzzy. Therefore, the perception is characterized by fuzzy rough computing. So you can try to model this fuzzy granularity characteristic of computation theory of perception using fuzzy rough computing concept. So it has a very future perspective. Let's consider about a perception of granule. Perception granule. So when you talk about perception, let's talk about a granule. Example, perception granule in a sentence, natural language processing. So perception granule, it could be a subject, predicate, and belief. For example, the flower is beautiful. This is a simple sentence. You get flower is beautiful. Here, what is the subject? So the description of the flower. What is the predicate? It's a beautiful. And what is the belief? That how strongly one believes to be beautiful. That how strongly the one believes that flower is beautiful. So this is what is called perception granule. Now, if you see that it involves two levels of precision. First of all, it's a beautiful. Whether it is a very beautiful, more or less beautiful, or so beautiful, level 1 precision. As level 2 precision is how strongly one. So belief with subjective probability that the flower is beautiful. Belief could be adverb or adjective or adverbial phrase. And here comes the significance of Z number, as explained by Professor Zade in 2011. It provides precision of semantics embedded in the sentence, precision of semantic messages, or representation of perception granule of the sentence. And we have defined Z star numbers, so augmented Z numbers. In 2004, one of our former PhD students, now she is a faculty in IIT Jodhpur, Romi Banerjee, which characterize the subjectivity, that is context, semantics, in order addition to what G number says, or abstraction active. That is, for example, when you're painting or you are writing a poem, you are having a constant thought. So we need to characterize the subjectivity, that is the context, semantics, in addition for abstraction of active thoughts. Here comes the Z number. Similarly, we have novel G number based thought processing in information science. One, we have a G numbers, data structure, thinking in managing proactive transaction, computer. So many papers have come out based on this. Very, very interesting topics for machine mind development. And then it comes to relevance to natural computation. So what is natural computation? As you explained, the granulation is a process like self-reproduction, self-organization, functioning of brain, Darwinian evolution, group behavior, self-membrane morphogenesis that are abstracted from natural phenomena. And F granulation, fuzzy granulation, is inherent in human thinking and reasoning process, and it plays an essential role in human cognition. Therefore, you see that F granulation is a new concept which is inherent in human thinking and reasoning process. That is one aspect you can deal. And one may note before I go, say original definition of soft computing or Lathizade had 4 components: fuzzy logic, neural computation, genetic algorithm, and probabilistic reasoning. Augmentation of the definition by introducing rough set as 5th constituent, the outcome of significantly the basic computational intelligence characteristics of soft computing, and therefore the foundation for the conception and design of high machine IQ. The third portion is relevant to big data analytics that we have been talking about for more than a decade, as I mentioned you. So here, uncertainty handling and granular mining point of view, what we have explained can be considered. And today we have got COVID-19 detection and screening from X-ray CT, where these techniques have been widely used for the last 2 years. We have seen so many papers coming out. Then granulated deep learning. Now, what is deep learning? Learning in depth in different stages. Learning in depth in different stages. Now, notice that since deep learning depends on becomes more meaningful because today we have got abundant of data, right? Same as machine learning. And the performance of machine learning or deep learning today, so let us consider it shallow learning in order to discriminate from deep learning. So performance of deep learning depends on the number of previous samples. Larger the number of samples, better will be the learning performance. However, larger the number of samples may create problem for engineering handling of the problem. Therefore, learning in depth, so therefore number of sample when you increase for increasing the learning mechanism, sometimes it becomes difficult to engineer the situation. Here comes the concept of how to reduce the number of learning, reduce the computation time. But definitely when you reduce the computation time, learning performance may be a little bit compromised. Therefore, the objective is reduce the computation time and improve the performance is the significance of granulated deep learning. That means without today, machine learning means deep learning, AI means deep learning, any kind of data because you have abundant of data. And if you have got some architecture also or one. So in a layman's sense, learning in depth in different stages. So it is an advanced form of machine learning. And since today we have got abundance of data, therefore it has choice of deep learning is meaningful and appropriate. However, since its performance depends on the number of previous samples, if you have larger number of previous samples or examples, is a better learning capability. However, increasing the number of samples increases the computation time also. Therefore, the challenging issue is how to reduce the computation time and as well as the improve performance. And here comes the concept of we introduced in 2018 the granulated deep learning reducing computation time. What do we do? In GDL model, instead of scanning the entire image pixel by pixel in the convolutional layer. So this is the GDL model. Here we have got an image, then we have got max pool, then we have got rectified linear unit. As you know, the CNN model. CNN model is basically famous for handling with image and video. Then the fully connected network, that means support vector machines and output. So here, if you have worked in CNN, here you for every pixel you put a filter. So in GDL, instead of scanning the entire image pixel by pixel, the convolutional layer, we jump over all these small granules. So here we do, instead of that, we first make it a granule. So when we move this filter over every pixel, we do it only once and then repeat the same value for others. Therefore, for a 32 by 32 image with n granules, where n is much, much smaller than 32 by 32, sliding the filter is done only n times instead of over 32 by 30 pixels. So hence a significant speed up is observed, compromising with some accuracy. So here see the comparative result of the one that is granulated deep learning using 3 by 3 granules, granulated deep learning using rectangular granules. This is a square granules, this is rectangular granules, but that is regular shape. Deep learning using arbitrary shaped granules, that is by region growing. And it is without granulation. You use CPU time, speed, it was 2.2 frames per second. Here it is 1.6. So speed has increased, but tacking speed has decreased, tacking accuracy. 74.6, 82. Accuracy of detection reduced. But let's consider these two, where not significant change, 82.25, 81. 70 is 81, 1.6, but frame is 1. And see the accuracy, granular deep learning, used by deep learning without granulation. The same laboratory data, you see the thing. See, same accuracy, you are getting percentage of the one. That is with granulated deep learning. Now let's come to this GDL framework is used not during training, it's used for only testing, because during training we use transfer learning or CNN. Now I will use another one. Let us now explain a granulated RCNN, that is a region-based convolutional neural network, and it's a granulated version, which is an improved version of the first RCN by extracting region of interest in this spatio-temporal granulation in deep CNN. That means this is an advanced version of faster RCN, of first extracting region of interest by incorporating spatio-temporal granulation, which improves performance during both training and testing. Therefore, improved real-time detection speed and accuracy. This is an example, just it has appeared in this month only, yesterday. So this is my network. I'm just last slide. So I have this. So here it takes the video as an input. Whereas other fast and faster, they take image by image. I take FT1, F2 of the serious special convolution pool 1. So this is based on AlexNet architecture based on CNN. And from that, I extract granule spatio-temporal. It's a temporal granule. I use spatio-color granule. Then I take the intersection. I continue spatio-temporal granule. So every time I reduce the number of pixels, but my region extraction becoming perfect. And then where I come in here, I extract the ROI map corresponding to this intersection. That means I reduce the further one. Then without this, for every pixel, I get this FTG formation, that anchor generation. And this anchor feature, I pass through fully connected network and this haunting box generation. So as a result, what is happening? Since I'm using videos, so it takes the video directly as input rather than static image. This is the first characteristic, different characteristic. Yeah, I'm using spatio-temporal granules for extracting region of interest, which is better than fast RCNN and faster RCNN. I'm using only granules formed over the pool 5 feature lab here, instead of all features in defining region of interest. So my number of feature is small, but it is well represented. Only positive ROI, that is ROI is denoting the object regions instead of the whole ROI map, is used as input to fully connected network. And while retaining the GRCNN and object classification. So it is very important. Only positive ROIs instead of the whole as input to FI. When we are retaining the GRCNN model, that is retaining the Alex model because of these new granules, and also for object classification. Similarly, only FT regions corresponding to this ROI instead of the entire FT map, feature map, for performing object classification. Therefore, improves real-time detection, speed, and accuracy. It is developed based on AlexNet architecture. Here, pool is always followed by linear unit. So, some results: significance of granulation during training. To take this faster RCNN and then granulated RCNN, And I take RPN, because when I take this only granular RPN, I call it RPN. When I take the temporal information, sorry, I consider it is FRPN. Obviously, it is expected that if I take temporal, it will give better result. So if you look at this, you have trained with image data, and look at this one. First RCN, GRRPN. If you take that one, mean accuracy precision has improved significantly compared to the one. However, the training time has increased because of the addition of this granule 1, granule 2. Similarly, if you take only the spatial information, and if you take the both spatial and temporal information gives better result. Here also you take little more time because you are taking. So GRCNN is superior to ATO in terms of training accuracy. GRCNN needs more training time than RCNN because of retaining the AlexNet for additional granulation, RY generation, and color generation. That's why. So GRRPN takes less time than GRFPN as it uses only spatial information and it does not granule 1, 2 for layer ATO. See, for spatial granulation, but for temporal, you need to use this one and this one also. There are two operations. That is what is replicated, 2 layers, hence learning of the ATO. GRFEN has higher accuracy rate for using additional temporal information. And this image has got 20 objects like car, bus, loco, truck, minivan, bike, transfer, etc. Similarly, if you go by this detection accuracy, that is the testing time, you see that first RCNN, AlexNet, first RCNN, then you have the first RCNN, then GRCNN. Mean accuracy 57, improved to 65 faster, and GRC 79. Similarly, first RCNN, GRPN. Here to increase here to increase here. So granulation in deep CNN, that means granulation RPN results in superior MAP score. That means RY pixels detected by RCN are more representative of the object cases. However, the test speed of RCNN faster RCNN 1.4 frames per second, 6.1. So faster has got better speed even from JS1. But for is faster, not faster. It's better than the fast one. Similarly, I can go FRPN, I'm not one. Now let's see some result. Say faster FRCN MACD, 6 frames per second detection speed. Within a just steel plant. It's all bike come. It's within a steel plant in India. Steel plant, it is a data. So its original speed was much higher, but we have slowed down to 10 frames per second, just to visualize this one. Similarly, the 6 frames here, detection speed, faster RCNN. Actual speed is detection speed is, tracking speed is 29 frames per second. But here we have reduced down to 10 figures just to demonstrate the detection capability. Similarly, we have got GRCNN. Here you see that red color were not detected by faster RCNN. It's a red color means these are only detected by the bike. They are not able to be detected by PBS maps. That is the beauty. This is a man, it's a person, bike. The red colors means were not detected by the first RCNN. First RCNN. This red bike. because in the first RCN they got merged, occluded, they could not be detected. So these red colors indicate one. Very nice result. Come is a paper. GRCN and RPN. So GRCN, FRPN, if you take the temporal domain, it is even better. So detection is red color. You see, they are not able to be detected by even GRCN. That is, GRCN even could not detect it. Previous one, red colors, not detected by F1, first RCN, but here the detector means it is not able to be detected by RCN, that is RPN, GRPN. That means by just considering spatial color is not enough. You have to take spatial temporal information. I'm showing again. This red color is coming out. Person, so they are all occluded. So many new objects are being tracked. And this was the original video, 29 frames per second. So fast. This was the original video, 29 frames. Previous views, we have reduced it. So this one I conclude in part. So evolution of the subject I'm mentioning. So pattern recognition, it was in 1960s. Image processing, 1970s. AI machine learning expert system, 1980s. But it could not survive much because you don't have abundant data and the computing power. The knowledge-based system in India, all over the world, it came in 1990s, India had 5 Nobel Center. Then data mining 2000, big data 2010. Now we are taking data-driven science, data science, data science. So in every one, we had new technologies. So new approaches for different tasks of pattern recognition to handle varying nature of data. So this is the mother subject. So if you want to know today deep learning, you have to know shallow learning. If you don't know shallow learning, you have to know neural networks, basic learning. If you have to know neural networks, you have to know pattern recognition. So one should not jump. And every evolution that is given birth of new terms and technologies. For example, here, when we came knowledge-based system, coverage system, we can have rule-based, case-based reasoning, your information retrieval, then soft computing, all the subjects were evolved because of the need. Then we have got big data. Now we are going about deep learning. It has a need to handle large data. But there is a big hope. Sometimes it is a false hope also. Why I'm telling you, say, when we started working in neural network in middle of 1980s, we had very big hope that it will emulate the information representative scheme of human brain. It will represent the biological nervous system. But then we realized it's not that easy. It's a highly interdisciplinary topic. So electrical engineers, computer scientists, one set up, we consider that it is a very good tool for working with any kind of data, because data, these tools are useful in the sense that it is adaptive to change in information. It is a robust, rugged, it's optimal, and it is parallel, that is speed. So all these characteristics any design engineer would love to have in his or her system. That's why based on them, and every tool has limitations, so we have integrated everyone. Another group was doing for mathematics. Then we see after 7 to 10 years, subject lost his interest because everybody expect too much money pumping from government of India, in our government also, all over the world, for market prediction, bank foreign currency prediction, then your gambling, then your health insurance. People jumped money because everybody thought that it is a tool available in the market, you buy and use it. No, life was not that easy. That's why subject collapsed. In the sense, money stopped We said because we didn't build the science behind it. We didn't build the mathematical foundation of those tools that time. That was our problem. I hope, and as a result, all neural network journal was not surviving. That's why IEEE Transition Neural Network, which is a premier journal, they changed the name to Neural Network and Learning System so that they can publish work from support vector machine. Similar neurocomputing neural network, they are publishing all other topics. I hope based on this previous example, because machine learning performance depends on the previous examples. So based on this, so learning from their previous examples, our deep learning will not wash out or lost interest soon. And that depends on our young researcher. That's my caution and that's my concern. So data-driven science research summary, it's concerned with the acquisition, storage, retrieval, processing, reasoning, mining, and finally conversion of data into knowledge. It's a huge challenge. It employs techniques, theories drawn from several fields like mathematics, statistics, information science, computer science, plus application domain knowledge. This is most important. So multidisciplinary. Has high potential from R&D perspective, both in academia and industry. In India, scenario is extremely encouraging with respect to job opportunity and initiative. With this one, I conclude. I acknowledge my all, because my all work 90% is done with my students and younger colleagues in India and abroad. Currently, I'm holding National Science Chair position, prestigious position of Government of India, and also my delivery talk is under AICTE Distinguished Chair Professorship. So some advice is not necessarily right. Okay. So I thank you very much. Stay safe and keep well, and wish you all a happy and better 2020. Thank you very much. Thank you. If you have any question now, I think I have taken enough time. I hope you didn't mind.
No problem, sir. Thank you. Thank you very much. Sir, we can take a few questions if I had asked to put in the chat box. So, or before that, should we take the photograph because that's necessary for the AICT? Dr. Shalaka, as the people put
Madam,
their questions.
just one sec. Yeah, just give me 2 minutes.
Yes, okay.
You can continue with the questions till then.
Okay, okay. So, if there are any questions, please put in the chat box. You can put your comments also.
The cameras can be on.
You can put your cameras on. So we have Dr. Kamal Shah, nice and informative session.
My camera
Dr.
is off.
Shilpa.
I don't know why.
Sir, your camera, at least we cannot see you now.
Yeah, I also just because I cannot just put it on. You can share your videos when you are done. So how to just do it?
So you have been all have been allowed to put their cameras on. So if you stop sharing screen now, maybe it will come in gallery view and you can stop sharing.
Okay. Stop sharing, right?
Yes, yes.
Stop sharing.
Yes.
Okay, yes. Thank you. Thank you.
We can see you now.
Thank you. Thank you.
Just give me a second.
Yes, Dr. Shalaka.
Okay, thank you.
Okay.
Did you take it? picture?
Yes, yes, she's
Okay,
taken.
Yes, sir. Yes.
Shalaka has taken picture. And I would like to thank Professor Shankar K. Pal for enlightening us on the various facets of machine intelligence, soft granular computing, and data analysis. You have gone right from basics, sir, and given very relevant examples and then to high-end applications. We also appreciate your efforts that you have taken for, putting in examples from the medical field as well as from drug discovery. Thank AICTE for choosing Bombay College of Pharmacy as the host institute. Our management and principal, Professor Krishna Iyer, who's also the convener of this distinguished chair professor lecture series, for their support. Our organizing team of Dr. Clara, Dr. Galvina, and Dr. Shalaka. Thank Dr. Vaishali Shesat for comparing the inaugural session. And also our team of Gajanan and Swati Pitkar for all the other support that we needed. Finally, I thank all the participants for their active participation and giving us even your feedback, because this is very, very important since we have to send this to AICTE. And I hope that we become one family, and for all future programs, that since we have your contact details, now we will be informing you of other programs that will be taking place at Bombay College of Pharmacy. Okay, sir. So we also have Vaishali Jadhav thanking us for the very nice session. And thank you, sir.
Thank you very much.
So the feedback link is put up in the chat box, and we request all of you to fill up the feedback before you leave the meeting. Also, the second point is that all those who have attended all the 3 lectures as well as submitted the feedback form will receive e-certificates. It will be done probably in a week's time after we finish with AICTE formalities. Okay. So you can have a look at the chat. People are appreciating.
Okay, thank you, thank you. Yeah. I was told actually by Dr. Bhenkot long back that when you give a talk, you please make sure that your host sends the feedback. So please actually remind also. So now I actually remember, yes, he also mentioned.
Sir, the thing is that the same day that we finish your lecture, we send everything to AICTE.
Okay, no,
so that's mandatory,
okay.
Sir. It's mandatory.
I know that
it's on
you are
the
very
same day.
seriously taken this.
So we keep it open for some time, the feedback link. And then once it's filled, then we have to send the photographs, then the banner. So every, whatever we put our initial welcome slide for today, that plus Dr. Clara does, from the feedback, she makes a collage of it, and then that is also sent across. I know it would have been nice if, we personally met, sir, at Bombay College of Pharmacy. But whenever you come to Mumbai,
Sure, I'll come
tap
and
on
let,
it.
let the actually just pandemic be over. Then actually
Yes,
definitely,
yes. Once
definitely under this AICT scheme, still I mean they're there. So I like to just visit your institute.
Okay, sir.
Thank you very much.
Thank you, sir. Thank you.
Thank you. Should I leave now with your permission?
Yes, yes.
Thank you.
Sir.
Sorry that
No
actually just
problem.
sometime
Thank you very much, sir.
the internet gave some problem with the one. I don't know what's happened. But anyway, it actually ended nicely. There was not much disturbance in the one. I think I have been able to try to convince about this entire research topic as much as possible lucidly, and I hope it will be beneficial to. I don't expect that every line and every topic you will be understanding all listeners, but at least given a recent up-to-date information up to just 2020. 2022, I have given this one. So now we can look at the other literature and books and then go through this one. Okay. Thank you very much.
Yes, sir.
Thank you. Thank you for all listening to me for this long hours for these 3 days at this during this difficult time, and you attended, organized nicely this gathering from Bombay, leaving your all other activities behind. Only one. Thank you very much. So with this, if you permit me, I can leave. Thank you very much.
Thank you. Thank you.